Now we are going to the next presenter in the same problem statement, radio link failure prediction, is IEC research. Do we have one on the call?
Yes, we are here.
Okay, over to you.
Thank you. Can you see my screen?
Yes.
Thank you. Good morning, good afternoon, or good evening to everybody. My name is Juan Samuel Perez, and I am the team leader of IEC Research. We're going to be talking about our approach to the radio link failure prediction problem using weather information. The IEC Research team is formed by many professors of the Electronics and Communications Engineering degree program, in the Dominican Republic. Here's our agenda for today. We're gonna take a look briefly at the problem statement and the needs associated with it. We're going to speak about our general strategy for tackling the problem, some details about the model that we proposed, some performance metrics of that model, and then we're gonna have some final remarks and then the Q&A session. This challenge required the use of AI and/or machine learning for the prediction of future radio link failure occurrences. And the hope of the organizers was that we could create prediction models that would be able to predict from 1 up to 5 days ahead in time. Radio link failure is an anomalous condition of microwave line of sight links that has been defined by Turkcell. So in this sense, it is not standardized anomalous condition. It has been defined by Turkcell for this problem, and they have defined it using threshold on standardized metrics or KPI, key performance indicators. And the prediction of the early prediction, right, of radio link failure can result in mitigated downtime or reduced service degradation to the subscribers because upon the prediction, the telecommunications companies can, for example, dispatch engineers to the field or make contingency plans on the network side. Now, the data set that we used for this problem was directly provided by Turkcell, and it contains an anonymized information associated to some meteorological stations and to the RF links of interest. And we have there a timeline of weather forecast and measurements that includes measurements of humidity and temperature, for example, a timeline of KPIs of the RF links that includes information like the link length or the received signal level. We also have in that data set a characterization of weather stations and RF site locations. And finally, and very importantly, we have some spatial information where we were given relative distances in between the RF sites and the meteorological stations. There were some particular challenges of the data set that were mentioned before by our colleagues. We have a significantly imbalanced data set with a small percentage of RLF occurrence. So it's a very rare event, however important. And there was some uncertainty in regards to the origin of the weather predictions, and that came up in some conversations for clarification that we had with the Turkcell team. Also, there was some missing weather stations forecast data, and an interesting challenge here was the alignment of spatial and temporal data for tackling this challenge. Now, the issue of how the meteorological conditions affect radio links has been very well documented in the literature, both academic and professional. However, many of these contributions don't include maybe models that are widely available, maybe openly available, and that provide actionable information so that telecommunications companies can use them, and as our colleagues were emphasizing, that allows them to take measures in advance. Now, our strategy was very simple. We understood this problem as a binary classification task, and we envisioned a simple model, as simple as possible, that would predict the occurrence of the radio link failure per mini-link ID. And that is, in the terminology of the problem, each end node of the radio link. And we decided to use as inputs the radio link KPI history of that end node and the associated weather forecast data. Now, the assumption here was that the KPI history of the radio link would contain information concerning the susceptibility to failure or degradation of the link, while the weather forecast, would provide information on the expected conditions the link would face in the immediate future. So when we built our model, we even made these assumptions even more simple. We for the KPI history, we only used the previous day's data, and for the weather forecast, we only used the next day's forecast data. And this data, this forecast was the one that provided information from the closest meteorological station to the RF site of interest. And our experiments and discussions in the team then supported the use of decision tree models so that we could maximize interpretability, which was highly stressed by the organizers of the challenge. We wanted to make our model robust against feature scaling issues, and we wanted to use the embedded feature importance capability of decision tree models for achieving a dimensionality reduction. Now, here are some details about the model that we proposed. We implemented it using the decision tree classifier from scikit-learn. It had a low depth, so a good level, good generalization capability. We used class weights, very simple approach for handling the unbalanced data set. And at the end, we only required 29 input features for the prediction. And this is very relevant because many of those features were one-hot encoded, were based on categorical features. Now, the performance on the true class, which is the one that I would like to emphasize for the training data set, was about 60%. And we can see that the percentage of samples of the true class was very small. This first data set was provided by Turkcell, and it was used for the training. On the second data set provided by Turkcell, we only used it for testing, and then the predictions on the true class were lower, were about 30%. However, you can notice on the confusion matrix that the samples that we had available for that testing were the number was very reduced. Some final remarks. Our model is as good as the weather predictions. The source of the weather forecasts, their accuracy and consistency are the most important characteristics that our model exploits. And during the development, we observed better results trying to estimate directly the RLF occurrence instead of intermediate estimates of the KPI parameters upon which it is based. Thank you very much.
Thank you so much, Juan, for the presentation. Right now is Q&A session, so over to you, Vishnu.
Thank you, Thomas, and very nicely put by Johan. Well, let me ask judges first. Any of the judges, you have questions for Johan? Yes, Nakao-sensei, please.
Yes, thank you for your presentation. I'm interested in your accuracy result. It's 0.9, and you use did you use the random forest, or that's just a simple decision tree? And you consider 29 features, you said? And what which feature is most contributing to your accuracy, the high accuracy? Can you tell? I'm interested.
Excellent question.
Yuan, you're muted.
I'm sorry. Thank you very much. Excellent questions. Thank you. So the accuracy that we obtained, the overall accuracy was about 90%. And in particular, over the true class, it was about 60%. And for getting these results, we didn't use any ensemble methods. We used a very simple decision tree, as I have presented here.
Yeah.
So the most important features, as you can see, according to this model, are the forecast of thunderstorms and rain, the height of the RF site, the historical data concerning the link unavailability. Those were the features that ranked higher in our tree and were the ones that we preserved when we used the feature, the dimensionality reduction, and we kept those 29 features.
Thank you. So if you use ensemble method, would that improve even further from 90% to even more? Because the last presentation reported like almost like 100% accuracy. And you know, if it is the simple decision tree classifier, maybe you can try random forest to increase the accuracy maybe.
Yes, that is what we expect. We expect that if we use more complex models like random forests or gradient boosted trees, maybe we would have a better performance than the one that we obtained. And maybe we could use models, we considered this in the team, we could use models that exploit the time series nature of the data set that we were provided. So maybe using recurrent neural networks could be a possibility. However, in this case, because of the expectations of the challenge, we prefer to provide a very simple, highly interpretable model. We understood, based on discussions in our team and with the organizers of the challenge, that this was very, very important for them.
Okay, very clear. Thank you very much.
Thank you, Nakar-sensei. Any other questions from judges? I don't see any. In that case, we thank Johan for the excellent presentation, and back to you, Thomas.
Thanks a lot, Vishnu, and thanks to the presenters.